All right, suppose you have a suspension on a small children's electric scooter. The child averages that's going to ride this scooter 20 kilograms on a spring that is rated at 40 newtons per meter and a strut that damps 80 newtons per meter per second. Initially, the spring is at rest, and a speed bump causes the spring to compress at a rate of 0.1 meters per second. Find the equation of the movement of the child on the scooter. Graph the solution. Is it what we expected? So here we see that we have a mass that's going to be 20 kilograms. We have a spring constant, which is rated at 40 newtons per meter. And we have a damping coefficient, some sort of strut suspension assembly that's 80 newtons per meter per second. And so again, we have some sort of scooter here. There's the handlebars on that scooter, and it's going to have some sort of suspension in here, some sort of spring between the wheels and the scooter itself. And then we're going to have a, of course, it's got to be a stick figure child. And the child is going to ride this thing down the street. Okay, great. So we also have our initial conditions. We have that y of 0 equals 0. The spring is at rest, so nothing's happened yet, but just bumped into a speed bump. It's going to cause the spring to compress at a rate of 0.1 meters per second. So our equation is going to be the second derivative plus b over m, which is 80 over 20. That equals 4. Y prime k plus k over m, 40 over 20, which is 2, and that equals 0. And our initial conditions are the initial position is 0, and the initial rate of change is negative 0.1. Why? Because it's going across a speed bump, it's going to compress at a rate of 0.1 meters per second. So that's moving in the negative direction. And okay, so here, let's go through our guess process again. So we see that it has the first derivative in addition to the second derivative in the original function. So our guess is of the form e to the rt. Its derivative is r e to the rt. Its derivative is r squared e to the rt. And you notice that the reason these squares are coming about is not because of the second derivative itself, but because of the chain rule being applied twice, which creates two factors of r. So that's an important thing to note. Just because you see a second derivative does not mean that involves a square at all. I know it's confusing because when we look at the second derivative, you want to read that as d squared y dt squared. It's not a square. It just means the derivative of a derivative. Fortunately for us, it works out to be leading into a square. So now substituting in for y double prime, so r squared e to the rt. For y prime, we'd have 4r e to the rt plus 2y plus 2 e to the rt equals 0. Once again, we'll factor out our e to the rt. R squared plus 4r plus 2 equals 0. And you can see here, again, this will never be 0. So our auxiliary equation is going to be r squared plus 4r plus 2 equals 0. This one is not as easily factorable because I can't really find two numbers that will add to 4 and simultaneously multiply to give me 2. So I can use quadratic formula here. And quadratic formula will tell me that, or again, I could use Wolfram alpha. Wolfram alpha, you just enter this equation in as it is, but let's just go ahead and solve it. Why not? So r is going to equal this on top negative b, so there's my b, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 2, divided by 2a, which is 2 times 1. So cleaning that up a bit gives me negative 4 plus or minus the square root of 16 minus 8 is 8 over 2. And so this is going to give me two approximations. We're gonna give them an approximate form. Mainly the reason we do this is because it's just easier to work with, and we're not having to be super precise to let's say 10 or 15 decimal places. So we'll say it's about negative 3.4, and R2, so that's going to be negative 4 minus the square root of 8 over 2. And negative 4 plus the square root of 8 over 2 will give me about negative 0.6. Perfect. So that gives us our solutions to work with. So now that we know what the R values are, I'm just going to go ahead and jump straight to the superposition theorem. It's going to be K1 e to the R1t, which is negative 3.4, plus K2 e to the negative 0.6t. Now remember, y1 is e to the negative 3.4t, y2 is e to the negative 0.6t, but by superposition, any constant multiple sum of the two functions is a solution. So this is my position, and story is the same. Position means we need to look at the initial position, which is 0. And when we plug in 0 for t, the beauty of working with exponentials is this is just going to become k1 plus k2. Now for the velocity function, the derivative of this is going to be negative 3.4 k1 e to the negative 3.4t minus 0.6 k2 e to the negative 0.6t. And we know that this is negative 0.1. This is going to give us negative 3.4 k1 minus 0.6 k2. And this is the system of equations that we need to solve right here and right here. And there we go, there's our value of k1 and k2. So we have as our final solution y equals k1, which is about 0.04 or 0.04 e to the negative 3.4t plus k2, which is minus 0.04 e to the negative 0.6t. Now once again, we should expect very similar behavior. That we're going to have decay in both terms. So as t gets infinitely large, well, y is going to approach, that term is going to approach 0. This is going to decay to 0. And so together we're going to see this spring mass system come to a rest. If we come back over to Desmos, we get something very similar. And this one's not super, this one's even a little bit less exciting because, well, that spring mass system just again compresses a little bit, comes back to rest. Does not do any stretching. The reason we can try to understand this, or the way we can try to understand this, is there's the damping coefficient is sizably large, and so probably what's happening is the system is a little bit overdamped. So there are such things as having an overdamped or underdamped system. So the other thing we should just point out is again checking those initial conditions by even just scoping out the graph, making sure that your initial position is 0, 0, and then because we have just a very slight negative initial rate of change, probably explains the difference between this massive oscillation here and just this very subtle oscillation. There's enough damping to where this initial velocity is just not very strong. Just imagine that you push a spring on your car just very lightly and with a very low speed. You're not going to get very much oscillation at all. So if we zoomed in on this, we could really make this pronounced. But you see that relatively speaking, this one almost compresses down to almost, what about 0.125, almost a quarter of a meter. This one doesn't come even close to that. Now at this point, we might have a hunch as to how we can solve a lot of these differential equations. So I don't want to just limit us to just talking about spring mass systems. This could be any second order equation where we have the second derivative plus some constant times the first derivative plus some constant times y equals 0. Now for us, this constant here is the damping coefficient divided by the mass, and this is the spring constant divided by the mass. But again, we don't have to limit ourselves to just studying spring mass systems. So one thing that we're speculating here is that the solution is going to have this form, k1 e to the r1t plus k2 e to the r2t. That's been our observation in the last two examples. Now what are r1 and r2? Well, those are roots of the equation r squared plus c times r plus d equals 0. So we do have that observation now that the coefficients of y double prime, y prime, and y are going to be the coefficients of r squared, r, and the constant term. And once we solve that, we have our value of r1 and r2 that satisfy the solution, and then we can solve for k1 and k2 using initial conditions.